when we talk about math modeling, and in particular the recommended practice of math modeling. So, anybody want to say anything at this point about the meaning of math modeling, beyond what we said this morning?
I just think it's when your students are able to show application of whatever problem multiple
Mhm.
ways. So if there's a
Mhm.
student learning about fractions, that they would be able to show it as numbers, as an equivalent fraction, as a picture, as whatever.
Sort of
they
like that
need.
question we had on the video this morning, what is 2/3 of a quarter?
Right.
Can you show that? Yes, yes, yes.
So something more concrete is what you're saying, rather than this abstraction. Is that what we're thinking?
Mhm.
And then we can abstract from that concrete.
The term math model has been used by mathematicians a long time, and when they talk about math models, they're referring very often to equations or sets of equations that describe the behavior of some phenomenon. And it's perfectly acceptable for us to think of a math model as an equation as well as a concrete representation that helps people understand the concept at hand, or a diagram, or a written explanation.
Like Northern's had a course, mathematical modeling.
Yes.
For years.
Yes.
You know, it's something that we've talked about, but we just haven't talked about it on the K-12 level.
That's correct, that's correct. And in fact, the course, which many universities have, involves using real-world problems for which an answer is not readily apparent and figuring out the math related to the answer. So when you think about a mathematical model, you're free to think of any representation of the situation that might come to that might come to mind. Also, there is that link to a real-world problem. That's another underlying component. So those are two things that you can keep in mind regarding math modeling. Go ahead. Here's a sort of a working definition of a math model. It's an attempt to bridge the gap between the math taught in the classroom and math needed to solve real-world problems. Think about that a minute. I think the math taught in the classroom is changing to be more in line with solving real-world problems. I gave a non-example and then a potential example. The airport is 28 miles from my home. How long would it take me to get to the airport if I drive 50 miles an hour? That would be a basic, I don't know if I'd even call it a problem for most 7th or 8th graders. If I know rate times time equals distance. But the potential example says that the airport is 28 miles from home. How much time, and that part that's blocked off, should I allow? How much time should I allow for driving to the airport, thanks Mary, from my home to ensure that I don't miss my plane? And that takes into account the driving conditions that may be affecting my commute, the time of day, the amount of other cars, all of the various factors that could affect my answer to this real-world situation. Both are legitimate questions to ask, but if we are going to include genuine real-world problems, then we bring with it all of the constraints that we may not have previously thought about in our problems. Go ahead.
Right now.
What I like about that
Go
problem
ahead.
is with those problems in the past, we would see a lot of the non-example. But as a teacher, you would get but what if it's raining? What if it's not?
Oh, I'm
All of
so glad,
those-
particularly middle school.
Yes.
Oh,
All of those great
come out,
thinking
and we dismissed them.
Right.
Yeah,
And
you
now
know,
there's a way to incorporate
to
them
validate
and
those.
have the kids build on them.
Yes, yes. So I guess this is sort of another example. I think of this as kind of a good problem. A pound of butter is typically sold in boxes of 4 sticks. The boxes usually measure 2 by 2 by 5 inches, and the sticks are arranged 2 by 2 in the box. Oh, this figure is very light. I hope you can see it there. Can you see it? Yeah. And And then, a certain manufacturer decides to sell the butter in a flatter carton, and he's going to arrange the sticks side by side. And I hope you can see that other figure there. Will the two butter cartons require the same amount of cardboard packaging? Explain why or why not. I'm not interested in having you solve this problem right now. Maybe we want to think through our head what would be involved in solving it, and then think about what kind of answer we would look for from our students. What would be involved in solving this?
Are we answering?
Yeah.
Okay.
Yeah.
I think I would first have to understand what the question is asking.
Yes.
So looking specifically at what, the question is, and then also looking at what information is given, writing questions as to what information I still need or I need clarified, and then coming up with some ideas on how to solve it.
What sorts of things might a student need clarification on with
Thinking of
that?
a
Yes.
good.
Oh, yeah.
If you're talking about how much cardboard you need, and the surface area, one thing that always bugged me about those problems is there aren't boxes built that perfectly measure the outside. There's always a flap.
Yes.
You have to
The
be
ceiling
able to
edge.
build it.
Okay.
Yeah,
The
and
ceiling
that
edge.
is
Yes.
Do you take
never
into
seems to be
consideration or not?
Included.
right,
in the-
which
yes.
always frustrated me because you need that to build,
Yes.
and that adds up
Yes.
to a lot.
What else? What else?
Is the butter in solid form or liquid form?
Oh, I hadn't thought of that one, but
Oh.
there will be a kid.
Middle school. They'll-
Yeah. We can go on. Here's the problem as a modeling problem.
That's the size of cardboard.
Yeah, that would need some explanation, wouldn't it?
Make an inference that it has something to do with plastic and
Well,
cardboard.
Yeah, I'm wondering how you combine those materials.
Make it 100 boxes. Yeah, I don't think that's true, guys. I can't imagine people lifting 100 pounds at a time.
Pallets.
Pallets, yeah, pallets,
Pallet
forklifts.
jacks.
I'm just thinking of the Food Network. Who's that lady that uses all the butter?
Oh, Paula Deen.
They're going to Paula Deen's.
Yeah, that's one recipe for.
Need to be in order to accommodate 100, and then we have to take into account the actual thickness of the container itself.
Right.
And if we have a flap that goes over the end, it's double thickness maybe. There are several things there that we have to take into account. So what I consider, well, pretty good problem, maybe boring, a pretty good math problem can become a modeling problem when we really acknowledge that in the real world, this stuff is going on. I'm ready.
Okay, or I like the Carol Dean. Is that Carol Dean?
Paula
Paula
Deen.
Deen.
Yeah, I've got a neighbor, Carol Dean, but Paula Dean, because that puts it in, more real world context with that.
Absolutely.
And it might pull a few more people into it, so it's just something you can, or the way you frame it, you just
Well,
to
you
give
can
it.
make a joke about it too,
Yeah.
so
Oh,
it
yeah.
makes them.
Butter?
Yeah.
And a fun task for this too is to give students 4 geometric shapes, and they have to figure out which shape you can get the lowest amount of surface area with the greatest amount of volume, because if you are working for a shipping packaging company, you want to save the company money, but at the same time you want to produce a really cool product because you have to make sure it has that wow factor in the
Absolutely,
store.
absolutely, yes.
Like the Toblerone chocolate bars.
Oh, yes.
Have you seen that video? There's a video on that.
Really?
Yeah.
Oh, cool, that's
Yeah,
another one
there
to
is
put on the
one,
list.
I think it's one of the Dan Meyer ones. but-
Probably.
Yeah, but it talks about that, and that's how he presents it.
Alrighty. So our plan is to help you understand modeling, what it is, why it's important. Become familiar with problem situations. We're gonna be in the algebra geometry context that can be used to motivate math modeling and suggest ways to integrate this. I think we're ready to go on that. Maybe you wanna speak to this, Mary?
Oh, okay, sure. All right, so we're looking at real-world situations, so we have real-world problems, which that packaging problem is a real-world problem. I I mean, you know, we buy things in packages, whether it's the potato chips being put in there or whatever it is, whether it's the butter. So how can we translate that into some kind of a math problem? Well, we did that on the last slide. We have to make some assumptions, right? We have to decide, you know, are we going to include the thickness? We're going to talk about the flap. What kind of a flap are we going to have? Are we going to think about something more of a net for the for what the
Container.
shape is? Yeah. So then we have to think about in the math model that we're going to come up with. Are we going to use equations? Are we going to use graphs? What are we going to work with here? Okay, and then we just, you know, can we interpret the solution, the results? And then we have our real world solution, and then we look back. Does it fit the problem? You know, as you said, you know, what about the flap? If we forgot the flap, how are we gonna put this together? Are we gonna tape it together?
Mhm.
Duct tape? No. But yes, and it kind of goes back again to Polya and his problem-solving approach. Are you aware of Polya?
Oh,
Yeah,
sure.
and the 4 steps. So, yeah, so it's basically that, you know, we just changed it around a little bit. Okay?
So to get you started, I wanted to show an example of what I call a slack rope cord. It's made by tacking a 15-inch of string onto a cork board without pulling it taut. So I've made this, and I've used this with eighth grade students in an exploration of function, actually. You know, I have to tell you the truth. I had the students measure out the string to be 15 inches, and of course they made it longer so we could wrap it around and everything. But I had some students who didn't realize or weren't sure when it was tacked on the board this way, whether or not it remained 15 inches long, honestly.
That's
No,
the
honestly.
track
Wow.
athletes. My track athletes will be at one stadium and then we go to another for
Mhm.
another meet and they are convinced that it
Yes,
is a
different
different
length,
distance.
yes. These things that seem so automatic for us are not for many students. In particular, this student happened to be from Mexico and he was in the United States. This was his 5th year in the United States. And he went back, his family went back and forth, and he missed about 2 months of school every year, you know. And through no fault of his own, he just hadn't had the kinds of experiences that allowed him to think about this. Well, that's the person I have in mind. What I asked the students to do in my naivete was to write an equation to represent the situation of the slack rope cord. Write an equation. Could you do that? Think about that a minute. What kind of equation could you come up with? Write an equation that represents this real world situation, where I have this string that hangs down. I can pull it taut at various positions, move those around various ways. It's an interesting situation. I found that it was not trivial to ask kids to write an equation at all. In fact, that's one of the points at which I became very interested in what has to happen between the real world situation and the equation model. What needs to happen there so that that can make sense? What do we got? What do we got?
Could you just do x plus y equals 15?
Yeah. Most of us who are pretty good at math write x plus y equals 15.
Well, I just said x equals 15 because the length of the string is
Okay.
15.
You could, the whole
That's
thing
the
is
o-
15. X equals 15, yes.
All I
Yes.
could really figure
Anybody
out.
else have anything essentially different?
Or I just call one part of the rope x and the other part 15 minus x and it equals 15.
Yeah, okay. Oh, I love that. X and 15 minus X.
I like that because I like everything in slope intercept form.
Oh, that's great. That's good for you. I mean that sincerely.
No, thanks.
I'll behave. Let's think about a minute. Let's analyze for a minute. What has to happen from your thinking about this string tacked on this board to writing an equation? And obviously there are multiple ways we can answer that, but what has to happen in a thinker's mind?
You minimally need to know that an equation has an equal sign.
Okay.
'Cause
You
there
need to know
is
that an
issues.
equation has an equal sign and what an equal sign means.
Yes.
Yes. Yeah. We're gonna talk.
Because
some about
expressions
that.
and equations seem to be interchangeable.
Blended. What else?
And 2 parts equal a whole.
Yes, it's not trivial, guys, that the 2 parts do equal the whole. Like I said, I had kids who weren't sure that this strength, I actually wadded it up and just said, is this 15 inches? I'm not sure. Interesting. What else? What do you think would be most problematic if you ask a 7th grade kid to do this?
Well, I automatically looked at it as a triangle, and so the
Oh.
first equation I wrote down was a squared plus b squared equals c
Yes,
squared.
I actually had a couple kids do that. They just, their little mind's eye filled in a 3rd side,
Mhm.
and they thought about it as a right triangle, so the a squared plus the b squared being c squared.
Mhm.
It was interesting because, there are positions where this looks pretty much like a right angle. You follow what I'm saying? That's not too good, is it? No, that's not very good. But I don't know if we get it. Maybe
It's pretty
yeah.
good, yeah, we got it.
About there, yeah. Just the idea that that little relationship only applies to right triangles, sort of thing. What I found was problematic for kids, if you don't mind my offering this, is the idea that they could call this A or X and this B or Y or 15 minus X. The whole use of symbolism is a huge jump for a lot of kids. Am I making sense?
Yeah.
Want to add anything?
I was just thinking your right angle there. I always put a corner of my paper.
Absolutely, absolutely.
Prove to them it's a right
Just-
angle. They always have one with them.
To demonstrate that it's truly a right angle. This activity is what really got me interested in how kids, middle school kids think about math, how they think about functions, how they use the equal sign, how they use other symbolism, how they see equality. And all of this that just, I as a learner, and I think many of us just were okay with, no big deal. But any of which can become the block for students attempting to make the link from a real-world representation to an equation model of the situation. So I'll have you advance a thank you. I don't think we need to do this. If we could look back at it though for just a minute.
I would totally do this with my sped kids.
Yeah.
They need to see that.
Mhm.
They can't, they won't make that jump.
I have found that making a table is one of the most effective models of a situation for helping kids make that jump to a formal equation. I call an equation formal. And just use your ruler, measure it. I'm always asked, why do you include this column for the total length? Why do you think?
Helps with the equations.
Yes, it helps with the equation. It helps that kid who wasn't sure that the length really stayed 15. So we can go one thing. These are questions that I don't think we necessarily have to answer this afternoon. Identify what's changing in the situation and what is staying the same. Go ahead. Amanda, go ahead.
Well, independent and dependent variables,
Yeah.
that's what you're leading into.
That is, it is.
And I like that you don't go straight to that. You start, because they don't think in
You
terms of
can't
independent
go
and
straight.
dependent. They
Mhm.
think of, this is good.
Yeah, and with this situation, which one does depend on which? It's interesting. Choose a way to label the changeables. I like to use that word initially instead of variable, because it emphasizes what parts of the situation are changing versus what parts are staying the same. And there it is, what the equal sign actually means in this situation.
I think sometimes with the equal sign where I think part of the reason students get confused is because we take expressions and then we simplify them. And when we stick the equal sign next to it, then we're making it into an equation, which
It's just
is
sort of
not an
hanging there.
equation. Yeah,
Yes.
which is, it's not an equation.
Yes.
So I think it's difficult, kids get, different meanings from that, and we tell them an equation has an equal sign, expression does not, and then we simplify an expression and we stick an equal sign with it.